The morning begins with that deceptive stillness only tropical coastlines can produce. Air hanging warm and heavy, water sliding over shallow sand in a rhythm so soft it feels engineered for relaxation. Palms lean toward the surf, throwing shadows that ripple in diluted blues, and tourists drift in with the same unhurried pace as the tide. At first glance, it is a place where danger seems incompatible with physics. Everything is too bright, too open, too harmless. Children splash in knee-deep water, parents idle in waist-deep shallows, and the sea is so clear that even the grains of sand look magnified beneath the surface. In these idyllic conditions, a predator like a shark or crocodile would be obvious. But the real threat today is almost perfectly invisible, drifting in from just beyond the sandbar. A box jellyfish, a creature built by evolution to remain hidden until the moment it kills. It moves with a quiet that borders on eerie. There is no fin breaking the surface, no shadow sliding across the sand. Instead, the jellyfish's bell, a transparent, cube-shaped dome with barely a hint of blue, pulses in slow, deliberate contractions. These movements look peaceful, almost fragile, but every pulse is part of a precise hunting system refined over hundreds of millions of years. Unlike most jellyfish, box jellies can actually swim with intention, using coordinated contractions to steer rather than drift. And unlike their more passive relatives, they possess clusters of complex eyes arranged around their bell, capable of detecting shapes, light contrasts, and even obstacles. They do not think as we understand it, but these eyes allow them to navigate shallow coastal waters with unsettling effectiveness, especially in calm conditions when the water acts as a magnifying lens for sunlight. The real menace, however, trails behind the bell like the faintest suggestion of thread, tentacles nearly invisible in the bright shallows, stretched out for meters. In certain angles of light, they disappear entirely, becoming a hazard as subtle as warm water. Each tentacle carries thousands upon thousands of microscopic weapons called nematocysts, capsules coiled with venomous harpoons under internal pressure so high that they are among the fastest cellular firing mechanisms on Earth. Crucially, these harpoons do not choose when to fire. There is no trigger in the jellyfish deciding to attack. The nematocysts fire on contact, reacting to chemical cues on the skin of fish or mammals. To the jellyfish, a human leg is just a large, slow piece of biology, a surface that activates the same chemical receptors as a struggling fish. When a tentacle brushes against skin, the reaction happens in millionths of a second. The microscopic harpoons blast through the outer layers of tissue, delivering venom designed to immobilize prey almost instantly. This venom is a complex biochemical cocktail engineered by natural selection to disrupt multiple systems at once. It tears open ion channels in nerve cells, causing immediate and often overwhelming pain. It destabilizes the electrical rhythm of the heart, making the organ misfire or halt altogether. It interferes with the respiratory system by sending muscles into spasms. Some victims of severe stings never make it back to the sand. The collapse is that fast. The jellyfish does not chase, roar, or strike. It simply drifts, makes contact, and the survivor, if there is one, tries to understand why their body suddenly feels like it is shutting down from the inside out. In the chaos of a sting, instincts betray you. Thrashing, kicking, and clawing at the water only worsen the situation. Movement causes the tentacles to wrap tighter, dragging more nematocysts over fresh skin. Every additional centimeter of contact multiplies the venom load. This is the trap many swimmers fall into. Panic increases exposure. Fish, the jelly's intended prey, often make this mistake too. Their frantic movements trigger widespread nematocyst firing along a tentacle, and the jellyfish exploits that mechanical chaos. The more turbulence a victim creates, the deeper the box jellyfish's influence penetrates. Stillness is counterintuitive in pain, but it is the one thing that limits further envenomation. Locals in northern Australia and parts of Southeast Asia understand this instinctively. Decades of coastal culture have taught them to freeze before they flee. From a biological perspective, the violence of the venom has nothing to do with aggression. It is simply efficiency. Box jellyfish need to disable fish fast enough to prevent them from tearing free and damaging the delicate tentacles. A fish that suffers cardiac arrest within seconds is a safe catch. Unfortunately, mammals, with our sensitive and conductive skin, are accidental victims perfectly vulnerable to this system. Even partial contact can leave wheals that welt into purple lines shaped exactly like trailing tentacles. Severe contact can send a healthy adult into cardiovascular collapse in the time it takes a wave to break. Yet box jellyfish are not villains haunting tropical beaches. They are apex drifters, organisms that fill a crucial role in marine ecosystems by regulating small fish populations, feeding turtles, and maintaining balance in nutrient-rich coastal zones. Their life cycle ties them tightly to the rhythm of warm seasons and rain patterns. After spending part of their life as tiny polyps attached to rocks and mangrove roots, they metamorphose into free-swimming medusae as temperatures rise. This is why certain beaches become dangerous only in specific months. Warm shallows with gentle currents, high salinity, and abundant juvenile fish draw box jellies in predictable pulses, and coastal communities often adapt their daily routines to these seasonal migrations. These rhythms shape local culture in ways outsiders rarely recognize. In northern Australia, beaches install stinger nets, mesh barriers designed to keep larger box jellyfish out during peak season. They are not perfect, but they drastically reduce encounters. Vinegar stations are placed along beaches because vinegar neutralizes unfired nematocysts, preventing additional venom release during first aid. Locals sometimes avoid entire stretches of coastline in dangerous months, even if the water looks flawless. The risk calculus becomes part of life. Weather patterns, wind direction, and water temperature all signal whether the sea is inviting or waiting. The illusion of safety is what makes the box jellyfish such a remarkable evolutionary success. It does not rely on ambush terrain, speed, or intimidation. Its power lies in the combination of invisibility and biological precision. The bell refracts sunlight in a way that erases its outline. The tentacles resemble strands of drifting algae, and the venom system operates on pressures and reactions so extreme that the jellyfish essentially weaponizes basic physics. In a world where many predators announce themselves with sound, shape, or motion, this creature survives by being almost entirely undetectable. For nature filmmakers, capturing box jellyfish requires patience and thick respect for their unpredictability. Cameras must maintain distance, and divers move with an unnatural calm, because one misplaced fin kick can bring a tentacle into a current and across exposed skin. Specialists who work in stinger territories develop a counterintuitive attitude, one rooted in slow, deliberate movement and an almost monastic understanding of the water's texture and patterns. They learn to read the subtle cues, the faint shift of underwater glare, the small irregularities in currents that suggest a jelly drifting near the surface, or the presence of juvenile fish clustering close to shore, hiding from something too transparent to see. What makes the box jellyfish fascinating is not that it kills quickly, but that it represents an evolutionary path built almost entirely around efficiency and subtlety. It is a hunter optimized not through strength or intelligence, but through the physics of membrane tension, chemical sensitivity, and biological pressure. It drifts where people swim, not because it is drawn to humans, but because warm, shallow waters are ideal for the small fish and crustaceans it consumes. Its presence near beaches is an ecological side effect, not a pursuit. And yet, its danger reshapes human behavior in profound ways. It teaches coastal communities to respect patterns invisible to tourists. It drives emergency protocols, seasonal beach closures, and long-standing cautionary traditions. More importantly, it forces us to confront an uncomfortable truth about marine ecosystems. Some of the deadliest organisms are the ones that leave no silhouette, make no sound, and give no warning. In the clear shallows of a perfect summer morning, while families step into the surf with sunscreen and snorkels, a box jellyfish may drift just meters away, its tentacles trailing in a loose lattice carried by the tide. Nothing in the water announces its presence. There is no ripple, no shadow, no pulse of color. Only the knowledge, for those who understand the ecology, that in certain seasons, in certain currents, the most dangerous thing in the ocean is the one you will not see until it touches you. The reef begins in soft gradients of turquoise, rolling downward into deeper blues that absorb sound and motion. Even in perfect visibility, the underwater world feels suspended in slow time. Fish weaving between corals with the steady rhythm of tides, rays gliding like drifting shadows, and shafts of sunlight breaking into shimmering mosaics that flicker across the sea floor. A lone diver moves through this landscape with deliberate calm, exhaling bubbles that rise in shimmering columns before dissolving against the surface. Nothing about the scene suggests danger. The water is warm, the reef is vibrant, and the creatures nearest the diver behave more with curiosity than fear. It is in this moment of quiet equilibrium that a sea snake enters the frame, slipping through the water like a striped ribbon caught in a gentle current. The snake's movement is fluid, in a way land snakes can only imitate. Its body, flattened into a narrow paddle, works with the water rather than against it, pushing in smooth lateral waves that require almost no effort. The diver watches, holding position, because the snake's approach is not a threat. Sea snakes rarely flee from people. They seem almost indifferent to human presence, sometimes even drawn toward bubbles or the reflective surfaces of equipment. Their eyesight is modest, but their sense of water pressure, motion, and electrical cues is refined. A combination that lets them navigate reefs cluttered with crevices and corals without wasting energy. In the calmness of this moment, the snake looks harmless, even delicate, its banded body catching rays of light that flicker across scales designed for a life spent entirely in the ocean. But beneath the quiet behavior lies a biochemical arsenal that belongs on a different battlefield. Sea snakes carry venom that surpasses most land snakes, not in theatrical aggression, but in precision. Land snakes often target mammals or birds, animals with complex circulatory and respiratory systems. Sea snakes hunt fish, animals that escape in fast bursts, vanish into crevices, or thrash violently when restrained. To stop such prey, evolution pushed their venom toward extremes. Their neurotoxins instantly disrupt the electrical signals that allow muscles to contract, while powerful myotoxins break down muscle cells at the structural level, turning tissue into a biochemical catastrophe. In fish, this system works almost instantly. Within seconds, prey lose control, their muscles failing as their bodies surrender to paralysis. For a predator that must chase prey through three-dimensional space, that speed is crucial. The irony is that sea snakes rarely inject this full firepower into humans, even when bites happen. Part of the reason lies in fang structure. Many species have small fangs fixed at the front of the mouth, and they rely on precision strikes rather than massive venom yield. Another reason is behavior. Sea snakes are not territorial in the same way many land snakes are. They do not defend ambush sites or protect eggs on land. Their world is fluid, literally, and conflict is expensive in the ocean. When confronted by divers, they often retreat, glide away, or observe with mild curiosity rather than panic. Yet bites do happen, and when they do, it is rarely in serene, controlled diving environments. The majority occur far from coral reefs and tourism zones, among fishermen working in the open sea. Trawlers and net fishers unintentionally scoop up sea snakes with their catch, pulling them onto the deck in heavy, tangled knots of netting and flailing fish. In that chaotic, thrashing mix on a wet boat floor, a snake trying to escape can easily strike if grabbed or stepped on. Fishermen often attempt to throw the snake overboard by hand, wanting to clear the deck quickly before the catch spoils or gear becomes damaged. It is in these rushed, unglamorous seconds that human error collides with a nervous animal's survival instinct. The danger of such bites is deceptive. Victims often report feeling almost nothing at first, a slight prick, or no sensation at all. Sea snake fangs are needle-like, optimized for slipping between fish scales with minimal resistance. The venom, too, acts quietly at the start. Neurotoxins begin disrupting nerve signals, while myotoxins break down muscle fibers at the cellular level. Inside the bloodstream, myoglobin, a muscle protein, spills into circulation as muscle cells dissolve. The kidneys attempt to filter this sudden flood of protein debris, becoming overwhelmed in the process. Hours after the bite, the victim may still feel fine, only to collapse suddenly as paralysis spreads and kidney function begins to fail. It is a slow, creeping catastrophe, beginning silently before revealing its damage. In the marine world, however, this biochemical intensity has nothing to do with aggression. It is simply precision shaped by evolutionary pressure. Fish can escape in milliseconds. A venom that stops them immediately prevents wasted energy. Sea snakes must breathe air, rising to the surface every half hour or so, depending on species and activity. That need for air places metabolic limits on their hunting. They cannot afford prolonged chases or prolonged struggles. A venom that ends conflict instantly allows them to feed efficiently, conserve oxygen, and minimize time spent near the surface where predators might lurk. One of the more extraordinary adaptations in sea snakes is how they manage life underwater while retaining the lungs of a terrestrial ancestor. Many species have evolved extended lung structures running the length of their body, allowing them to store more air and regulate buoyancy. Some can absorb oxygen directly through their skin, supplementing what they inhale, a trait rare among reptiles and extremely useful in long dives. Their bodies, slender and streamlined, move with hydrodynamic grace, but the mechanics behind that grace reveal how deeply evolution pushed them into a marine niche. Even mating, a behavior often clumsy for land snakes, becomes a coordinated spiral underwater, where males track females through chemical trails carried by currents. Despite their potent venom, sea snakes seldom kill humans. Most bites are what herpetologists call dry or low venom strikes, defensive rather than predatory. A snake lashing out on a boat deck is not trying to kill a human. It is attempting to break free. The amount of venom delivered in such situations is often minimal because the snake is not anchored onto prey or aiming for a full envenomation. Geography also plays a role in why fatalities are rare. Fishermen who work in sea snake territory often recognize symptoms early, and coastal medical centers in regions like Southeast Asia, India, and Northern Australia typically stock anti-venom. But luck, as always in ecology, remains a factor. A well-placed bite from a species like the beaked sea snake or the olive sea snake can deliver enough venom to cause severe paralysis, rhabdomyolysis, and kidney failure, outcomes that remain life-threatening without rapid intervention. Observing a sea snake hunting reveals even more nuance to its biology. It does not rely on speed alone. Many species work reefs with methodical precision, senses attuned to subtle cues. They probe crevices where eels and small fish hide, using tongue flicks and pressure sensitivity to read the environment. Their venom is so effective that even prey making a desperate sprint are often overtaken by paralysis before reaching shelter. The snake then locates the immobilized fish through a combination of smell and mechanoreception, consuming it head first to avoid fin spines. Its feeding strategy is efficient, structured, and completely indifferent to the drama humans often attribute to venomous animals. In terms of ecological role, sea snakes function as mid-level predators that regulate reef fish populations, particularly small schooling species and reef dwellers. They compete with predatory fish, reef sharks, and some seabirds, forming part of an intricate web of energy flow on tropical reefs. Because they spend much of their life in shallow to mid-depth waters, they also serve as indicators of reef health. Declines in sea snake populations often track with overfishing, reef destruction, and pollution, a reminder that their quiet presence is tied to the stability of the entire ecosystem. The diver watching the sea snake on the reef understands none of this in the moment, nor needs to. What matters is the unspoken rule shared by experienced marine explorers. Move slowly, give the animal space, and respect its curiosity. The snake swims closer, investigates the diver's reflective mask, and then drifts away with the same calm that brought it in. There is no tension, no threat, only coexistence in a world where each creature follows the logic of its evolution. The snake's venom, deadly on paper, remains unused. Its grace, not its danger, defines the encounter. If there is a lesson hidden in the slow glide of a sea snake over a reef, it is that danger in the ocean is often a byproduct of adaptation, not intent. The venom that can cripple a human in hours exists because fish evolved to flee, reefs evolved complexity, and predators evolved precision. Humans simply swim through this evolutionary conversation, sometimes too close, sometimes unprepared, but always as outsiders. The sea snake is not a threat waiting to strike. It is a specialist operating at peak efficiency in a niche that predates human presence by tens of millions of years. And in that quiet, drifting moment where diver and snake share the same water column, the ocean reveals one of its most enduring truths. Not all deadly animals are aggressive, and not all harmless-looking creatures are safe. The sea snake glides onward, disappearing into the blue, carrying within its slender body a venom powerful enough to rewrite neuromuscular function in seconds, a chemical masterpiece built for a very different audience than us. Shallow tropical water has a way of encouraging carelessness. The sunlight turns the surface into a glassy sheet, revealing the sand below in perfect detail. Every ripple of the tide magnifies the grains, patterns, and scattered rubble, until the sea floor looks almost ornamental, like a curated aquarium. Small fish flicker across the frame, disappearing into pockets of coral before re-emerging in brief flashes of silver. The water is calm, warm, and only waist-deep, the kind of place where snorkelers relax, where surfers wade out with boards under their arms, where children run ahead without hesitation. It is precisely in these serene, unthreatening conditions that one of the most dangerous fish on Earth lies waiting, not through intention, but through perfect invisibility. The camera glides over an ordinary patch of sand and rock. Nothing moves. A cluster of algae-covered stones lies scattered around a small depression in the sea floor. For several seconds, the scene invites the viewer to mentally check out. It is simply too mundane to trigger instinct, but as the shot lingers, shapes begin to betray themselves. The stone in the center has a slightly irregular outline. A subtle texture does not match the rest of the rubble. Two pits, eyes if you know what to look for, reflect a faint shimmer of light. Then, almost imperceptibly, the animal exhales. What looked like rubble resolves itself into a stonefish, a master of camouflage whose entire survival strategy is built around the art of not being noticed until something stands too close. Stonefish are ambush predators in the purest sense. They do not patrol reefs in search of prey. They do not chase, stalk, or intimidate. Instead, they settle onto the substrate, bury themselves lightly in sand, or position their bodies among rocks so convincingly that even experienced divers sometimes fail to recognize them until the animal moves. Their bodies are armored with warty, algae-like skin textures that mimic encrusted stones. Their coloration changes slowly over days to match local substrate. Evolution shaped them not as sleek hunters, but as fixtures of the reef, living landmines armed with some of the most potent venom known in any fish. When prey approaches, the stonefish's ambush strike is astonishingly fast, belying its sluggish appearance. The mouth, normally a tight line blending into the body, can expand with explosive speed. The strike is not a graceful arc, but a sudden vacuum. The fish inhales a volume of water so rapidly that the prey, often a small fish or crustacean, is pulled into its mouth before it realizes anything has changed. The entire event, from the first twitch of motion to the disappearance of the prey, often lasts less than 6/100ths of a second. Cameras must run at high-speed settings to capture it. The stonefish returns to stillness immediately, settling back into its disguise as if nothing happened. This ambush lifestyle explains why stonefish ended up with another notorious adaptation, a venom delivery system that targets one very different type of threat, a creature far larger and heavier than the prey it eats. The stonefish's dorsal spines rise like rigid stakes along its back, each connected to venom sacs that activate under pressure. This system did not evolve for predation, it is purely defensive. Large predators in the reef, sharks, rays, large groupers, pose real threats to a slow, sedentary fish. When stepped on, bitten or crushed, the stonefish cannot flee. Instead, it relies on a mechanism that punishes pressure with instant retaliation. Humans, of course, step on them far more often than any natural predator. The venom itself is a biochemical weapon designed to make any predator regret the attempt. When weight drives a foot or fin down onto the spines, the sharp points penetrate deeply, pushing venom into tissue. The reaction is immediate and overwhelming. Victims describe the pain as outpacing severe burns, fractures, even childbirth. It radiates through the limb in waves, expanding into a systemic assault that includes swelling, intense inflammation, tissue necrosis, and a dangerous cascade of cardiovascular stress. In severe cases, the venom disrupts nerve signaling and can send the victim into shock or cause temporary heart irregularities. The spines themselves can snap under pressure, breaking off inside the tissue, prolonging the injury even after initial treatment. Yet the stonefish is not an aggressor. It does not lunge at swimmers or chase intruders. It merely exists in the exact environment where humans like to tread: warm, shallow, calm water near reefs and sandy flats. Surfers walking out to break zones step on them. Divers entering or exiting water cross their territory. Fishermen handling nets in estuaries sometimes scoop up a stonefish hidden among the catch. These events are accidents of coexistence, not intent. Real cases highlight the consequences. Surfers have been hospitalized after stepping on stonefish while wading over reef flats, unable to paddle back through the pain. Divers have lost consciousness on beaches as the venom overwhelmed their cardiovascular system. In some remote areas, where antivenom is not immediately available, untreated stings have resulted in permanent tissue damage or even amputation. Yet fatalities today remain rare thanks to rapid medical care and the availability of stonefish antivenom, one of the most widely used fish antivenoms in the world. The antivenom, however, is only part of the story. Prevention in the water is simple but often ignored. In regions where stonefish are common, locals shuffle their feet when wading through shallow water. The motion pushes sand and debris forward, signaling a disturbance that alerts hidden animals or causes stonefish to move just enough to avoid the direct step. Protective reef boots, thick-soled and sturdy, can prevent spines from penetrating far enough to deliver a full envenomation. These small behavioral adaptations, learned through generations of coexistence, transform a potentially lethal encounter into a non-event. Biologically, the stonefish sits at an interesting intersection between vulnerability and lethality. It is slow-moving and heavily reliant on camouflage for survival. A fish with such limited mobility is always at risk from faster predators. Hence the evolution of both its perfect disguise and its punishing venom. Its role on the reef is more nuanced than simply deadliest fish. As an ambush predator, it regulates populations of small reef dwellers. By consuming fish that graze on algae, it indirectly influences coral health. Its sedentary habits create microhabitats and hiding spots for smaller organisms. The stonefish is not merely a threat, it is a functional, integral part of the reef ecosystem. Observing one closely, once the mind adjusts to seeing the animal rather than the stone it pretends to be, reveals a creature adapted down to every detail. The eyes, though small, are positioned high on the head to scan upward for prey. The mouth faces forward, hinged for instantaneous expansion. The pectoral fins act like stabilizing hands, allowing the fish to brace itself against rocks or prop itself up slightly when adjusting position. Even the venom system, terrifying in human contexts, is simply an evolutionary solution to a problem of being too slow to escape predators in the busiest ecosystems on Earth. The tragedy and the irony is that humans are not the predators this system was designed for. We are just large, heavy shapes passing through environments where stonefish have hidden for millennia. The fish does not want confrontation. Its venom is a last resort, activated only when force is applied. In many cases, divers report that stonefish tolerate being brushed or nudged lightly without triggering the spines at all. It is pressure, a foot planted directly atop the animal, that unleashes the full response. The underwater world does not advertise its dangers. The bright colors of the reef distract the eye. The clarity of shallow water creates false confidence. But the stonefish, lying motionless among rubble, forces a different kind of awareness, one grounded not in fear, but in respect for the subtlety of marine evolution. It reminds us that the most dangerous animals are not necessarily the ones that chase, roar, or display aggression. Sometimes they are the ones that never move at all, relying on the blindness of those who assume danger must be visible. As the camera pulls back from the stonefish, the viewer sees the environment again: sand, rubble, coral fragments, all perfectly ordinary. The fish has blended once more into the scenery, vanishing in plain sight. The next wave rolls across the shallows, and nothing suggests a threat beneath the surface. But for those who understand the reef, the lesson is clear. Every step in these waters is a negotiation between life forms sharing the same habitat. The stonefish, armed with camouflage and defensive venom, is simply one participant in that complex conversation. And in the end, it is not the stonefish's venom that defines the risk, but the assumption that the seafloor is empty. Low tide exposes a stretch of shoreline that feels almost childlike in its innocence. Tide pools dot the rock platform like scattered mirrors, their surfaces trembling as small waves creep in and retreat. Sunlight refracts off shallow water, turning each pool into a miniature world where hermit crabs scuttle between pebbles and juvenile fish hide beneath drifting fronds of seaweed. Tourists wander barefoot between these pockets of life, bending down to pick up shells polished smooth by years of abrasion, taking photos of starfish and anemones, and reaching without hesitation into crevices where small creatures retreat from the bright midday light. Nothing about this landscape announces risk. It is the sort of place parents let children explore freely, confident that danger belongs to deeper waters. It is within this deceptive calm that the blue-ringed octopus thrives, a creature small enough to curl into a seashell, delicate enough to be crushed by a careless hand, and yet carrying venom potent enough to stop human breathing in minutes. At rest, it is almost invisible. Its skin displays muted browns and soft yellows that blend into the surrounding rock and sand. Each tentacle adjusts to contours of stone with quiet precision, allowing the animal to mimic its habitat so effectively that even seasoned marine biologists can miss it at a glance. It does not flaunt its presence. It relies on remaining unnoticed, passing through the intertidal zone like a whisper. Only when disturbed by a probing hand, an approaching predator, or a sudden vibration does the octopus reveal its true identity. Iridescent blue rings bloom across its skin, shifting from faint outlines to electric halos in fractions of a second. These rings pulse with an intensity that seems almost artificial, as though powered by tiny bioluminescent batteries rather than pigment cells under neural control. The transformation is not just a visual threat display. It is a communication system evolved to warn anything nearby that this tiny creature is not to be touched. For many predators, this is enough. The rings broadcast a clear message. There is danger within this softness. Inside the blue-ringed octopus's salivary glands lies tetrodotoxin, a neurotoxin so powerful that a volume smaller than a raindrop can paralyze an adult human. Tetrodotoxin works on a fundamental principle of nerve function. It blocks voltage-gated sodium channels, the microscopic gates that allow nerves to send electrical signals. Without those channels, messages from the brain cannot reach the muscles. Breathing becomes impossible, not because the lungs fail, but because the diaphragm stops receiving instructions. The victim is not unconscious. They are trapped inside an unresponsive body, aware but unable to move, speak, or inhale. This is the most chilling biological detail of all. Paralysis arrives before the mind shuts down. People bitten by blue-ringed octopuses sometimes remain fully conscious as their respiratory muscles cease to function. They hear voices, feel themselves being carried, sense the panic around them, yet cannot respond. It is a rare window into the terrifying neutrality of nature. An animal too small to notice delivering a toxin that rewrites the rules of consciousness and body control. The octopus does not deploy this venom recklessly. Its primary diet consists of small crustaceans and occasionally fish. The toxin allows it to immobilize prey quickly, preventing injury from struggling crabs or darting fish. It bites with a small beak tucked beneath its body, releasing the toxin into tiny animals that succumb within seconds. Humans, vastly larger and not part of its evolutionary targets, suffer the consequences only when an octopus feels trapped or severely threatened. A hand reaching into a rock pool may mimic the pressure of a predator, pinning the animal, picking it up. Imagining it to be a harmless curiosity increases the risk even further. Despite its reputation, the blue-ringed octopus does not seek confrontation. It spends much of its life avoiding danger, slipping from crevice to crevice in search of food and shelter. It is a creature defined more by caution than aggression. Its size, often no larger than a golf ball, makes it a target for fish, octopuses, and wading birds. Its defense relies on camouflage first, warning second, venom third. Most individuals never bite anything larger than their prey. Fatalities in humans are rare not because the venom is weak, but because encounters that lead to bites are uncommon and usually involve people unknowingly picking them up. The lack of anti-venom adds gravity to any bite. There is no chemical treatment that neutralizes tetrodotoxin inside the body. The only effective response is artificial respiration, oxygen delivered manually or via medical equipment, maintained continuously until the toxin is metabolized and excreted. This process can take hours. If oxygen supply is sustained, the victim recovers fully, as the toxin does not damage the brain or nervous system permanently. Without that support, respiratory arrest leads quickly to brain damage or death. It is a fragile balance between time, preparedness, and proximity to help. In ecosystems where blue-ringed octopuses are common, such as Australian and Southeast Asian tide pools, locals adapt behaviors that tourists often do not. They avoid placing hands into unseen crevices. They flip shells with tools rather than fingers. They recognize the faint patterns and body outlines of resting octopuses long before any blue rings appear. This quiet cultural knowledge, passed through fishermen, divers, and coastal communities, acts as an informal safety net that protects both humans and octopuses from interactions that would end badly for both. From an evolutionary standpoint, the octopus's reliance on toxin rather than speed or armor reflects the pressures of its habitat. Tide pools are transitional spaces, too shallow to provide escape routes, too variable to guarantee cover, and too dynamic to allow long-term hiding. An octopus in this environment must remain adaptable. Its camouflage relies on chromatophores capable of rapid color change, allowing it to match sand, algae, or rock equally well. Its body can compress to fit into cracks smaller than its own head. Its arms coordinate with remarkable dexterity, probing and manipulating the landscape with spatial awareness that rivals the tactile capabilities of primates. The nervous system of an octopus is distributed, with a significant portion of neurons located in the arms rather than the central brain. This architecture grants each limb a semi-independent control system, enabling complex problem-solving at the limb level. It is one of the reasons blue-ringed octopuses hunt so efficiently in tight spaces. Their arms sense texture, pressure, and chemical cues directly from the environment, responding with precision faster than the central brain could manage alone. Yet, this intelligence comes with vulnerability. Blue-ringed octopuses live short lives, often no more than a year. Females die shortly after laying eggs, investing their entire remaining energy into guarding the clutch until the young hatch. During this period, the female does not hunt, feed, or defend herself aggressively. She is a guardian reduced to a biological imperative, slowly weakening until she collapses. Her offspring begin life in miniature versions of the same tide pools, inheriting both the camouflage and the weaponry, but none of the experience. Many will be eaten before reaching adulthood. This cycle makes the species perpetually in need of high reproductive success to maintain populations. For nature filmmakers, capturing blue-ringed octopuses presents a paradox. The most iconic behavior, the glowing blue rings, occurs only under stress. Ethical filming requires respecting the animal's safety, avoiding harassment or provocation. The best footage is often found accidentally, a natural encounter between predator and prey, a territorial display toward a rival octopus, or a response to environmental disturbance like a wave surge or shifting rock. Filming them in calm, unlit states reveals their true nature far better, delicate, cryptic, and blending seamlessly into the landscape that shelters them. The real danger, then, is not the octopus itself, but the ease with which humans underestimate it. The animal does not project menace. It does not roar, sting visibly, or loom. It sits quietly in a shallow pool, no more threatening than a seashell, until a hand closes around it. The blue rings flash only when it feels there is no escape. By then, the proximity is already too close. As the tide returns, washing over the rock platform and merging the pools back into the ocean, the blue-ringed octopus slips into deeper water. The sand shifts, covering its tracks. The landscape resets, becoming once again a playground for wandering hands and curious eyes. The danger remains invisible. A tiny animal, fragile yet armed with a toxin that paralyzes nerve signals and leaves consciousness intact. It is a reminder that the boundaries between safe and lethal in coastal ecosystems are often microscopic, drawn not by size or sound, but by biochemical precision. And in these quiet, glittering tide pools, the smallest creature often carries the largest consequence. The estuary at first light is a study in stillness. The tide is halfway in, pushing murky brown water across mangrove roots that twist like ancient knots above the mud. Thin mist clings low to the surface, drifting between the trunks and reflecting the pale glow of the rising sun. At a casual glance, nothing moves. The water is flat, opaque, and deceivingly calm. A sheet of liquid silence, broken only by the faint tapping of mud skippers along the bank. A fishing boat sits tied to a ramp where the river mouth meets a sheltered bay, its hull touching water so quietly that even ripples refuse to form. It is exactly the kind of scene that convinces people the dangers of the tropics are exaggerated. But beneath the surface, inches below the film of light, lies a presence so large and motionless that the water itself seems unaware of it. A saltwater crocodile, nearly 5 meters long, floats with only its nostrils and eyes nearing the air. The rest of the body is submerged in perfect suspension, muscles relaxed, tail stretched behind in a gentle curve. For an animal often framed as a charging monster, its signature move is actually the opposite: absolute stillness. The crocodile is not waiting for a specific target. It is waiting for opportunity. And in estuaries like this, opportunity comes to the water's edge every day. The crocodile's ambush strategy is a masterpiece of energy efficiency. By remaining motionless, it conserves heat and oxygen. Its heart rate slows to a crawl. Its sensory world sharpens. Pressure receptors along its jaws detect even the faintest ripple, and its eyes, adapted for low light, read shapes with clarity even in muddy water. Crocodiles do not rely on sight alone. They interpret the world through vibration. A single footstep on the bank sends signals through the water like a beacon. This is why the water appears empty until the moment it isn't. When people step near the edge to launch a kayak, wash hands, collect bait, or simply enjoy the view, the crocodile does not need to stalk or creep forward. It is already in position. What follows is one of the most explosive movements in the animal kingdom: a lightning-quick lunge from still water. The crocodile uses the full length of its tail as a lever, pushing off the riverbed or the water itself in a vertical thrust. The body becomes a projectile. In a fraction of a second, what seemed like a patch of calm river erupts into a surge of scales, teeth, and muscle. This burst speed is not theatrical. It is physics. Crocodiles can accelerate with such force that their entire mass rises out of the water in a single arc. This is how they take birds from low branches, pigs from riverbanks, and fishes from the edges of boats. The lunge ends not with a slash, but with a bite, the most important moment in a crocodile's hunt. A saltwater crocodile's bite force is among the strongest measured in any living animal, surpassing that of lions, sharks, and even other crocodilian species. The jaws act not like cutting tools, but like industrial clamps. The teeth themselves are conical, built for grip rather than slicing. They interlock through flesh, cloth, bone, and muscle, locking the victim into an inescapable hold. This design reflects an ancient evolutionary truth. Crocodiles do not need to cut their prey. They only need to hold it. Once the jaws close, the outcome is effectively decided. The victim is pulled backward into the water with a single, practiced movement. Crocodiles do not waste energy wrestling on land. The water is their arena. There, their mass becomes an anchor and their body becomes a lever. Their tail swings with mechanical precision as they initiate a death roll. This rotational attack is not a dramatic flourish. It is a technique optimized to tear, break, and destabilize. The roll disorients prey, breaks limbs, and compromises the spine or joints. Even large animals like buffalo and boar cannot resist the torque. For humans, the force is catastrophic. The roll is not meant to kill outright, but to subdue and reposition. Death, for the prey of a crocodile, usually comes from drowning. Crocodiles do not suffocate their victims intentionally. They simply keep them underwater, using their weight and bite as restraints. Struggling burns oxygen faster, and panic accelerates the process. The crocodile does not release, because releasing is not part of the plan. Once the victim stops moving, the animal shifts into the next phase of its strategy: storage. Crocodiles often stash bodies beneath logs, submerged vegetation, or the undercut banks of rivers. These makeshift larders protect the carcass from scavengers and allow time for decomposition to soften tissues. In the tropical heat of northern Australia, this process happens quickly. Softened flesh is easier for the crocodile to tear into manageable pieces. It is a system refined long before humans appeared, a methodical continuation of a hunting style unchanged for millions of years. This quiet brutality explains why so many accidents occur at seemingly harmless locations: boat ramps, fishing platforms, swimming holes, and even backyard riverbanks. In Northern Territory and Queensland, warning signs are standard, yet incidents continue. Fishermen leaning over to wash bait buckets, campers collecting water for cooking, tourists stepping into shallows for photos, kayakers launching from mud banks without checking the water first. In nearly every case, people describe the water as looking completely safe. The camouflage is not visual. It is behavioral. Saltwater crocodiles do not patrol with dramatic motion. They do not announce their presence with splashes or waves. They float, wait, and then strike with precision that feels almost unfair in its efficiency. Many survivors report that they never saw the crocodile until the instant of impact. Even experienced locals speak of the silent zone: water that seems too still, banks too quiet, mangroves too dense. They know these are signs, not comforts. The saltwater crocodile's dominance also rests on its extraordinary physiological adaptations. Its body is essentially a biological hybrid of endurance and explosive power. Its musculature is designed for sudden ambush, not long pursuits, yet its lungs can hold air for over an hour when it remains still. Its armor-like scutes act as solar panels, heating the blood beneath to regulate body temperature. Its sensory pits detect minute vibrations and pressure changes, giving it a radar-like awareness of movement. Even its brain structure supports ambush behavior, prioritizing instinctive precision over complex strategies. In ecological terms, the crocodile occupies a position few predators achieve, an apex role that spans both freshwater and marine ecosystems. It can hunt in mangrove channels, estuaries, rivers, floodplains, and open coastlines. Its diet ranges from fish to birds to pigs, wallabies, turtles, and water buffalo. This versatility, combined with territorial aggression, means that no waterway in northern Australia can be considered reliably free of crocodiles. Locals assume the opposite. Every waterway is a crocodile waterway, unless proven otherwise. Yet despite their fearsome reputation, crocodiles are not indiscriminate killers. Most attacks occur because humans enter their space at the wrong time or place. Crocodiles do not hunt humans as primary prey. Humans simply behave like prey at the water's edge. Their silhouette, their splashing, and their bending posture resemble vulnerable animals from a crocodile's perspective. The predator responds with the instinct it has perfected over tens of millions of years. And for those who survive, the encounter leaves a clarity that reshapes their understanding of wild landscapes. They speak of the silence, the speed, the absolute certainty with which the crocodile executed its strike. They describe the moment the water erupted, the crushing pressure, the disorientation of the roll, and the realization that escape was not part of the design. Many say the crocodile was invisible until it was already upon them. A recurring reminder that the greatest danger in the tropics is not the animals you see, but the ones that see you first. As the morning brightens over the estuary, the crocodile beneath the boat ramp shifts slightly, almost imperceptibly, adjusting its position as the tide continues to rise. It has not eaten today. It may not eat for days. Energy conservation, not constant hunting, drives its behavior. It will wait, patient as mud and roots, for the next ripple that signals opportunity. And in these waters, opportunity never takes long. Because for a saltwater crocodile, success is not measured in the chase. It is measured in the single moment when stealth becomes impact. When the water surface breaks, the jaws close, and the story ends before the mind even registers what happened. The ocean at dawn looks deceptively peaceful from the surface. The water is calm, broken only by slow rolling swells that catch the early sunlight and scatter it into mirrored streaks across the waves. A lone surfer waits beyond the break, legs dangling in the cool water, board rocking gently beneath him. To the human eye, the world seems shallow, a blue sheet with a bright horizon and little else. But a few meters below, the water thickens into gradients of shadow where light fades quickly, colors vanish, and outlines dissolve. The surface becomes a ceiling. The surfer becomes a silhouette. Below that silhouette, a great white shark cruises through darker water, its body moving with the slow, effortless precision that only apex predators achieve. There is nothing frantic about its motion. Its tail sweeps in wide, measured arcs, conserving energy while maintaining perfect control. The shark's world is a sensory landscape far richer than what sight alone can offer. The lateral line running along its body reads the vibrations of distant swells. Ampullae of Lorenzini, electroreceptors scattered across its snout, detect the faint electrical signals of muscle movement above. Even without looking up, the shark knows something is on the surface. A shape, a pattern, a disturbance in symmetry. It does not attack immediately. Great whites are not reckless killers, they are evaluators. They test, interpret, and then commit with extraordinary precision. This shark circles wider, rising slightly with each pass until the silhouette above becomes clearer. From below, the shape resembles a wounded pinniped, the shark's preferred prey. The surfboard and human legs mimic the proportions and movement patterns that seals display when resting or struggling. From an ecological standpoint, this is not an error. It is pattern recognition shaped by millions of years of predation. When the shark finally accelerates, the shift is explosive. A creature that drifted like a shadow suddenly becomes a biomechanical missile. The entire body engages. Massive red muscle along the flanks contracts in coordinated waves, the tail beating with bursts powerful enough to push the shark upward at speeds exceeding 40 kilometers per hour. Water shears around the head, turbulence shifting from a gentle wake to a forceful surge. The shark ascends from the blue gloom like a torpedo, jaws slightly parted, trajectory aligned with the silhouette overhead. This upward ambush, the signature of great white hunting, relies on physics as much as biology. Striking from below gives the shark the advantage of surprise, momentum, and gravity. The victim has no opportunity to see the approach. The shark's jaws, powered by massive adductor muscles, snap shut with a force capable of fracturing bone, tearing muscle, and removing entire limbs. The teeth, serrated and triangular, function like natural saws, slicing through tissue with brutal efficiency. The first hit is not always meant to kill outright. In natural hunting scenarios, great whites often deliver an initial massive strike to incapacitate prey before circling back. A seal, bleeding heavily and disoriented, becomes far easier to handle. This strategy, however, has devastating consequences when humans are struck. The initial impact alone can cause catastrophic injury, deep lacerations, arterial severing, traumatic amputation, or massive blood loss. The shark may release immediately after realizing the prey is not a seal, but by then the damage is done. The violence of that single moment defines the outcome. This is why great white shark attacks, although rare, are often life-changing or instantly fatal. The vector of attack, Speed, angle, and force means the victim experiences the full destructive capacity of the shark in seconds. Unlike crocodiles, sharks do not drown prey, and unlike snakes, they do not rely on venom. Their strategy is mechanical: hit, tear, incapacitate. For humans, surviving such an encounter depends on luck, immediate rescue, and proximity to medical care. Yet the rarity of these attacks deserves emphasis. Humans are not typical prey. Sharks encounter thousands of surfers, swimmers, and divers annually without engaging. Most great whites avoid humans entirely. They investigate, turn away, or continue on their migration routes. Many scientists argue that most bites are cases of mistaken identity or exploratory behavior. The shark testing an unfamiliar object with the only sensory tool it has for tactile evaluation: its mouth. The tragedy is that an exploratory bite from an animal weighing 2 tons has consequences far beyond curiosity. The great white's hunting strategy is deeply tied to its physiology. It is a regional endotherm, capable of elevating its internal temperature above that of surrounding water. This adaptation grants it faster muscle contraction, sharper neural processing, and more efficient digestion. Cold-blooded sharks are powerful. Warm-backed great whites are on another level. Their sensory systems, metabolic rate, and muscle performance allow them to pursue fast, agile prey like seals and sea lions in frigid waters where most predators cannot operate effectively. This warm-bodied edge influences behavior on a broader ecological scale. Great whites undertake long migrations, traveling thousands of kilometers between feeding grounds and breeding areas. Their movement patterns follow seasonal shifts in prey abundance: seal pupping seasons, whale carcasses drifting offshore, tuna schools moving across oceanic fronts. These migrations complicate human safety efforts. A beach that is safe 1 month may be part of a shark corridor the next. Communities along shark-prone coastlines use a combination of methods to reduce risk. Shark nets, despite the name, do not block sharks entirely. They act as fishing devices, catching and killing sharks and other marine life indiscriminately. Drumlines, baited hooks anchored offshore, have similar ecological drawbacks. Modern alternatives focus less on killing and more on tracking and awareness. Tagging programs use satellite and acoustic transmitters to monitor shark movements in real time, sending alerts to lifeguards and beach authorities when tagged individuals approach populated areas. Drones offer aerial surveillance, scanning clear shallows for large shapes. These systems do not eliminate risk, but they shift public safety strategies away from culling and toward coexistence. The reality beneath all these measures is that the ocean is not a controlled environment. It is a dynamic ecosystem where predators operate according to evolutionary logic, not human schedules. A surfer silhouetted against the morning sun is not entering a danger zone. They are entering someone else's hunting ground. Yet even in these waters, the likelihood of a fatal encounter remains low compared to everyday terrestrial hazards. The risk feels immense because the scale of the predator is immense, not because the frequency matches the fear. To close the episode, the camera pulls away from the lone surfer above and the great white below, revealing the vertical distance between them, a thin layer of water separating 2 worlds. This perspective mirrors the thread running through all 6 animals in this series. The box jellyfish drifting invisibly in shallow surf. The sea snake weaving gently through coral with venom designed for fish. The stonefish hiding in plain sight on the sea floor. The blue-ringed octopus, no larger than a child's palm, carrying enough toxin to shut down the human respiratory system. The saltwater crocodile waiting silently at the water's edge, its entire strategy condensed into a single explosive strike. And now the great white shark, rising from darkness with a hit that rearranges everything in a single moment. Size becomes irrelevant. Intent becomes irrelevant. What connects these animals is efficiency. The capacity to deliver a one-shot outcome through stealth, venom, mechanics, or speed. Some kill through overwhelming biochemical precision, others through bone-crushing force. All share the same principle. In the right circumstances, a single moment determines everything. As the great white circles back into deeper water, the surface once again becomes calm. The surfer, oblivious to the predator that came close but did not strike, continues scanning the horizon for the next wave. The ocean resets itself, vast and indifferent, holding within it creatures whose survival depends on precision rather than malice. And the lesson across all 6 chapters becomes clear. The deadliest encounters are rarely the ones you see coming. They are the ones built into the design of the animals themselves.